Welcome to the Lecture 7 for Physics 4C. In this third set of lecture videos on physical optics, we introduce a calculational tool that will help us with the wave interference calculations in this chapter, and which we will use extensively once we start our coverage of quantum mechanics in about a month. Complex exponentials used to model oscillatory phenomena is this tool. And unfortunately, very few lower division physics textbooks cover this topic with the amount of time and detail that is necessary, particularly for those of you who will be continuing your studies in physics or electrical engineering in the upper division, where this is an indispensable calculational simplification in your toolbox. The set of lecture videos here are self-contained and should teach you everything you need. But for those of you who prefer a written reference, the best, and only at our level, reference I have found is the Feynman Lectures on Physics, Volume 1, Chapters 22 and 23. I won't read the whole chapters out loud, although I recommend these chapters for your perusal. Let me refer to some key sections within these chapters. In Chapter 22, Feynman gives a review of algebra. While you might think, I know this stuff already, I recommend a careful read-through for a reminder of things that you do know, and a re-presentation of things you thought you knew, but maybe didn't know as thoroughly as you could, and probably would once you study these topics in the upper division coursework. The key moment in this chapter comes in section 22-5, complex numbers. In the fourth paragraph, immediately after equation 22.6, if you are skimming, he says, now the problem is how to compute 10 to 1 imaginary power. What guide is there? We may work over our rules until we can go no further, but here is a reasonable guide. If we can compute it for any particular s, we can get it for all the rest. If we know 10 raised to I times s for any one s, and then we want it for twice that s, we can square the number, and so on. But how can we find 10 raised to I times s for even one special value of s? To do so, we shall make one additional assumption, which is not quite in the category of all the other rules, but which leads to reasonable results and permits us to make progress. When the power is small, we shall suppose that the law 10 raised to epsilon equals 1 plus 2.3025 times epsilon is right, as epsilon gets very small. Not only for real epsilon, but for complex epsilon as well. Therefore, we begin with the supposition that this law is true in general, and that tells us that 10 raised to I times s is equal to 1 plus 2.3025 times I times s, for s approaching 0. So we assume that if s is very small, say 1 part in 1024, we have a rather good approximation to 10 raised to I times s. I recommend that you follow the rest of his reasoning process, which ends in equation 22.9. We summarize with this, the most remarkable formula in mathematics. E raised to I times theta is equal to cosine theta plus I times sine theta. This is our jewel. This is what we remind you in our lecture as Euler's formula. It's easy to mistake Euler's formula for an arcane piece of complex algebra with no real applications. That is why I recommend chapter 23 as well. In chapter 23, Resonance, Feynman applies complex numbers to harmonic motion. I recommend the whole chapter to you, but let me read a small portion for a peek at his insight. From section 23-1, Complex Numbers and Harmonic Motion, second paragraph. We are going to apply complex numbers to our analysis of physical phenomena by the following trick. We have examples of things that oscillate. The oscillation may have a driving force, which is a certain constant times cosine omega t. Now, such a force, F equals F naught cosine omega t, can be written as the real part of a complex number. F equals F naught exponential of I omega t. Because exponential of I omega t is equal to cosine omega t plus I times sine omega t. The reason we do this is that it is easier to work with an exponential function than with a cosine. So the whole trick is to represent our oscillatory functions as the real parts of certain complex functions. The complex number f that we have so defined is not a real physical force, because no force in physics is really complex. Actual forces have no imaginary part, only a real part. We shall, however, speak of the force f naught times exponential of I omega t. But of course, the actual force is the real part of that expression. Let us take another example. Suppose we want to represent a force, which is a cosine wave that is out of phase with a delayed phase delta. This, of course, would be the real part of f naught times exponential of I times parenthesis omega t minus delta. But exponentials being what they are, we may write exponential of I times parenthesis omega t minus delta as exponential of I omega t times exponential of minus I delta. Thus, we see that the algebra of exponentials is much easier than that of sines and cosines. This is the reason we choose to use complex numbers. In our lectures, we will introduce complex exponentials along a similar line as Feynman has in his lectures. And we will work through some examples expressing real-valued trigonometric functions using complex exponentials. Then, we are going to apply this newly introduced tool to the calculational problem that we solved last week, working out the intensity of a double-slit interference pattern. I hope you will see the power and simplicity of this approach compared with last week. And we will wrap up the second half of this lecture set working out the intensity pattern of single-slit diffraction. While your textbook also works this out using the geometric approach of phasor diagrams, I believe our approach using complex exponential algebra is much easier to understand without losing anything you need to fundamentally understand for your coursework in the upper division and beyond. We have one more lecture remaining in physical optics. In the next set of lecture videos, we will cover diffraction grading and other applications of optics.
And what I want to show you is that there's one general mathematical tool that you can bring in once and use it for all this different stuff. So this is the kind of mathematical tool that you would use if you are doing something similar to this, dealing with oscillation in an upper division level engineering or physics class. And it starts out with something that I keep saying this, but very few people seem to remember it. Something that you are supposed to have covered in pre-calculus trigonometry. It starts out with this Euler's formula, which says e to the I theta, meaning exponential of imaginary number I times some variable theta, is equal to cosine theta plus I sine theta. Do people remember seeing this? Euler's formula, outside of physics 4b, where you would have seen it when I brought it in. Wait, did I bring? Yeah, I started doing this 2 semesters ago, so all of you should have seen it if you took my 4B. But even if you haven't, you saw this in trigonometry, right? Yeah. And now that you have taken calculus 2, you can actually prove this. Let me just say how without doing it, taking time. You can prove this using Taylor polynomial. Write out the Taylor expansion of cosine theta. Write out the Taylor expansion of sine theta. Write out the Taylor expansion of exponential while being mindful of this fact. I raised to the power of 0 is 1. I raised to the power of 2 is minus 1. I raised to the power of 3 is minus I. I raised to the power of 4 is plus 1 again. And then it repeats from then on. So when you write out first 8 terms or so. Then you will see that this left-hand side is equal to this right-hand side with this I, giving you all the terms that still have I left in it. I skipped I raised to the power of 1. So this I will give you all these terms with the I still in it. And you can show that for yourself in like 20 minutes just writing it out. Good? Okay. Does anyone need any explanation of Euler's formula? So this is it's the first example you see of something that mathematicians do a lot, where they extend a known special function to a greater domain than when they were originally introduced. When they originally introduced the exponential, that was as a limit of, I guess, e to the x was introduced as a limit of n going to infinity. What is it? 1 plus x over n raised to the power of n, something like that? Is that right? Yeah, when x is 0, this is 1, x is 0, this. Yeah, so that's how it was introduced initially, right? And what you can realize is that even though when they were originally introduced, it was in the context of interest rate or whatever, x was just assumed to be real. But when you look at this, there's no reason to assume that x is real. Nothing forces you to. So x could easily be imaginary. And when it's imaginary, you could imagine this being I theta. And when you do that, this is the formula you get. That e to the I theta, and sort of working out the consequence of writing this out, you get that you could re-express this in terms of 2 real functions, or 1 real function, cosine theta, plus imaginary number times sine of theta. And mathematicians prove this, so I won't go through it. I don't have the time and I don't want to. So the reason I bring this in is because of the intuition about complex numbers, and is in particular periodic functions that this particular representation provides. Let me first show you the intuition about complex number that this provides. And the guide here is the fact that when you write this out, you get cosine theta and sine theta. When you hear the word cosine theta, what do you think about? Like, what's the first thing that you associate with the cosine of an angle? Adjacent? Okay, that's one. Sorry, I'm trying to do something that I normally stay away from. So when you say adjacent, you are talking geometrically, without figures, without having defined any coordinate axis. Right? Let's say we are dealing with a coordinate axis, x and y. When we say cosine of an angle, which axis are we talking about? X, right? So this cosine theta, which multiplies to the real component, 1, you can sort of naturally associate that with x-axis. And something similar for sine theta. So when you have a point, let's say a particular point here, which is at some distance r, then if I'm talking about 2D plane, XY plane, this is how you would describe this. I have some vector r, and the x component of vector r, this is angle theta. X component of this vector would be r cosine theta, and the y component of this vector would be r sine theta. Right? Everyone here has pretty good intuition about geometry. And what I want to tell you is that I can use this same exact figure and change just a couple labels to show you something that you have seen in the context of complex numbers. I can say, instead of this being the x-axis, this is really the real axis. Instead of this being the y-axis, this is my imaginary axis. You have actually seen this before. And if you have a point here, the way it would be introduced in your math classes, this point is, it has coordinates A and B, or you would express that as A plus IB. Is this sounding familiar to anyone? And with this coordinate representation in mind, you could say that this is the Cartesian representation of the complex number. This A would be the, this would be the X component. And this B would be the Y component. And what this can give you is it's the polar representation of a complex number. So let's say you have this complex number here that you can express in two different ways. Complex number z. The first time you saw it this way. You saw it as A plus IB. Right? This is what we can, I don't know if your math teachers use this language. This is what a physicist would call Cartesian representation of this complex number, or rectangular representation, because you have x and y coordinate. Yeah? And if we have a vector, so it's representing the x and y coordinate. Second way of expressing the same complex number is, instead of specifying the component, I can give you, I still need two parameters, but I choose parameters differently. Instead of x and y components, I give you length and direction. That's the polar coordinate. When you are talking about vectors, length r pointed in some particular angle, theta. That's what that representation in the physical vectors is. You can think of complex numbers being similar. Instead of this being A plus IB, I can write it out as length r times e to the I theta. R gives you the length of the vector. So this is the polar representation. R gives you some kind of length of a complex number. And e to the I theta, well, the theta gives you the direction of that, the complex number, if you can say that. Let me write out one last term that will maybe help make the connection more concrete. Let me just plug this in and expand it out and write out what it is. So plug this in and expand it out. This is what I get. R times cosine theta plus I times r sine theta. This is my, or rather this is my x component. Or since we're talking about complex numbers, this is the real component. And this is my y component, or my imaginary component. This one-to-one match is direct. It's anything you can express as two-dimensional vector, you can express it as a complex number. And anything complex number can be used to represent any two-dimensional vector. There's This is not some spurious connection I'm making. It's a, so the complex plane that you have seen, that is the geometric representation of a complex number. And to make the geometric aspect more concrete, this is the thing that would make the geometric features more clear. Yeah?
Doesn't that imply that e to the I theta is never going to be bigger than 1? Or
No, theta can be anything, because then theta wraps around, right? Sine theta, like theta can be 1,000,000.
but e to the I theta, that gets capped, right? Because
Um,
sine theta.
So you want to be able to say this. You want to be able to say, when I have e to the I theta, that it defines a unit circle. That somehow when you square it, that it's never going to be, it's going to be actually exactly 1. That's what you want to say, right? Now here's that's a good intuition. So that's what we want to do. Let me just point out the slight difficulty that you run into, and we will find a way around it. So the slight difficulty that you will initially run into is, let's imagine calculating e to the I theta squared. So I have e to the I theta, and let's say I just want to square it. So it would be equal to, well, let me plug this in. So cosine theta plus I sine theta. Take that, square it. It's equal to, so cosine squared theta. This thing squared, so that would be minus sine squared theta. And then there's the cross term, cosine theta times the sine theta. There's 2 of those. There's I2, so it's a plus 2I cosine theta sine theta. Is this what we wanted? Like, does this fit with this description that we are using? Not quite, right? Couple things are. So we wanted the length of this to be 1. We didn't want it to be function of direction. So, what all that this is showing is that apparently this is not equal to length. So the operation that you need to get length of a complex number is a different operation. Let me close that blind while you're thinking about it. The glare's in my way. Like, what other mathematical operation would you do so that you get something that has the correct property for length? Do you guys cover absolute value or modulus of a complex number in trigonometry?
Conjugated number. Conjugated number of the
Yeah. So this is the operation that's defined in that you define as a modulus or whatever. So let me just refresh your memory. So when you start dealing with a complex number, take the complex number squared. That actually doesn't mean much. That's not used very often. That's in contrast with a real number squared. Because a real number squared gives you always positive number. But if this is complex number, this is not guaranteed to be positive. I mean, look at it here. If sine theta is bigger, then this number will become negative. So the operation that is defined when you start learning complex number, using complex numbers more, is something absolute value squared is defined this way. It's defined as the complex number multiplied with something called it's a complex conjugate. And this is how complex conjugate is defined. Complex conjugate is defined as, I don't know, it's easier to describe it in words. Take all imaginary numbers in G and turn it into minus I. That's what complex conjugate is. So for example, if G is equal to A plus IB, where A and B are real, that's important, then the complex conjugate is A minus IB. Okay? And what I want to claim is that this complex, this absolute value squared here, this is equal to length squared. And let's see if this has the correct property that we need for length. Let me do the same calculation that we did here. Instead of this being, I guess, g squared, so or e to the I theta squared, what it would be is g, so e to the I theta times the complex conjugate. So it would be e to the minus I theta. Theta is real, so I can just do that. So e to the e raised to power of x times e raised to power of minus x. That feels to me like 1, isn't it? Everyone here feels comfortable with this particular calculation? If you do, great. If not, on your own time, try expanding this out. You will see that when you expand it out this way, this becomes plus, and the cross terms actually cancel out. So cosine squared theta plus sine squared theta, that is 1. So you do get so this does represent a unit circle, or the points along the unit circle.
So this is inverted version of Euler's formula. So in Euler's formula, this is what you've seen, that if you have a complex exponential, e to the I theta, then this can be broken down and written as cosine of theta plus I sine theta. And this is something you might have seen in pre-calculus, and after having taken calculus 2, which is a prerequisite to physics 4b, you should be able to actually prove this using Taylor polynomial. I'll take this as a given that this is an expression that you are familiar with, and that you at least have seen this formula. Now, what I want to do is I want to represent cosine of theta and sine of theta in terms of complex exponentials. And I guess this is one of those cases where it's easier for you to just see the formula first and see that it's true, as opposed to trying to derive this formula. So let me just write it down. This is the complex exponential representation of cosine theta. So cosine theta can be written this way: e to the I theta plus e to the minus I theta, and then I have to divide it by 2. If you have never seen this, let me show you that this equality here is true. So the way to show it is, let me just write out the right-hand side and see what I get. So as I write out the right-hand side, I'm going to use Euler's formula. So it's cosine of theta plus I sine theta, and then plus cosine of, I guess, minus theta plus I sine minus theta, whole thing divided by 2. And this is where it's very useful for you to know the properties of cosine and sine function. Cosine is an even function, meaning cosine of minus of a parameter, it's actually same as cosine of just a parameter. So I can ignore this minus sign without any consequence. I can do this because cosine is an even function. In a similar way, sine is an odd function, so I can pull out this minus sign, kind of. So with those modifications, this is the expression you see. So I'm just imagining pulling out this minus sign so that it looks like this now. So you see that you can combine some terms. I can add the cosine theta terms together because now they are cosine of the same parameter, and the sine terms cancel out because it's the sine of the same parameter, but one with a minus sign and one without. So when you finish the calculation, I have 2 cosine theta divided by 2. So yeah, the right-hand side is cosine of theta.
And you can get similar representation for sine theta. Sine theta could be written as in this way. I think once you have seen this, then you might already have some inspiration for how to write sine theta in terms of complex exponentials. So if you have it already, great. If not, let me write it down, see if it makes sense. E to the I theta minus e to the minus I theta. And I think I have to divide this by 2. Wait, not 2, 2i. And I'll leave that up to you to show that this expression really is equal to sine theta. It goes through the similar calculation. What changes is before it was the sine term that canceled out. With this change of sign here, it will be the cosine term that cancels out. And after sine terms, you add them together, this cancels out the factors that you don't want on the numerator. So this is the complex exponential representation of the trig functions. And with this, you don't need any trig identities. Let me just do a few and to see how with simply this information at hand and knowledge of exponential algebra, that any calculation you might have done using trig identity, you can also do using this complex representation of trig functions. Now, one mistake I made in the past semesters was that I was trying to derive these identities using this, and that's a little bit harder. What is easier is to show that the identities hold. Like once you already know the identity, then you can prove it using this representation. And the fact that you can prove it also means that you don't really need the identities themselves. Because if you simply go through the exponential algebra, you would get the same result anyway. So let me go through a couple of those examples. I guess let me start out with something simple, an identity that everyone knows, the identity that that's basically the Pythagorean theorem. I don't know if it has any better name than that, but it's this one that I'm thinking of. Identity that says cosine squared of theta plus sine squared theta is equal to 1. I'm calling this Pythagorean theorem because that's kind of what it is. If we have a vector r that has component x and rx and ry, then rx squared plus ry squared is equal to r squared, and that kind of comes from this. So let me prove that this is the case. You might have already seen a proof of a Pythagorean theorem that's geometric and uses all these things that you don't normally think about. The thing about the geometric arguments are they are clever, they are in some sense intuitive, but they are so difficult to come up with. It takes some smart person a lot of creativity to come up with a particular geometric proof. The nice thing about algebra is that you just follow a set of simple rules step by step, and you don't really need a lot of creativity most of the times, and you get the right result. And that's the advantage of using these expressions here, that something that might have needed geometric reasoning, you can get through by using purely algebra. So let me do it here. I'm just going to substitute in for cosine and sine these expressions that we got for cosine and sine. So let me do that. I have e to the I theta plus e to the minus I theta divided by 2. This is cosine theta. So let me say that this thing squared. So that's a cosine theta squared plus, let me write down the sine theta squared, e to the I theta minus e to the minus I theta. And here I'm just following all the rules of algebra strictly. I'm not doing any complex conjugate stuff because really this thing that I've written, if you say this is f of theta is cosine theta. So
even though this expression has i's appearing all over the place, it's a real function. So I shouldn't have to. So I'm not taking any complex conjugate. I'm not doing anything that that you haven't heard of. So let me go through the algebra. So squaring the first term, it's matter of expanding out the it's expanding out this expression e to the I theta plus e to the minus I theta times e to the I theta plus e to the minus I theta. So let me do that down here. Um, so the first terms together, that's e to the 2 I theta. I'm skipping some steps, it's the e to the I theta times e to the I theta, and when you add the exponents together, this is what you get. And let me multiply these two terms. That also gives me e to the minus 2I theta. And then I'm going to handle the cross terms. There's this term times this. That's going to give me e to the I theta times e to the minus I theta. So that's going to be 1. So that's 1. And this term times this, that's going to actually give me the same value, e to the minus I theta times e to the I theta. That's 1. So those terms added together, I have plus 2. So that's the first square. Let me write down the second square term. This time I'm going to do most of this in my head. I have the first term squared, so it's going to be e to the 2 I theta. I have the second term squared by itself. It's minus e to the minus I theta times itself, so it's going to be plus e to the minus 2I theta. And then I have the cross terms. That's the product between the first and the second term. And there's 2 of those, and I get, so that's minus 1 for one of them, plus e to the I theta times minus e to the minus I theta. The exponents cancel out, but I have plus 1 times minus 1, so it's minus. There are 2 of those, so minus 2. The denominator, I have to be a little careful here. It's oh wait, I spotted a mistake. This should have been 2 squared. So 2 squared is 4. I have 2I squared, and that's 2 squared times I squared. I squared is minus 1, so it's minus 4. All right, I got some simplifications to do. Let me do it here. I'm going to pull out this minus sign out front here so that it's super easy to miss the minus signs in the denominator. So I want to make sure I don't miss that. So with this minus sign here, I can kind of see what terms will cancel. I have e to the 2I theta divided by 4. I have minus e to the 2I theta divided by 4. That's going to cancel. I have the same thing happening with the second terms. They're going to cancel. So I have 2 minus minus 2 or plus 2 divided by 4. So that gets me 4 over 4 or 1. So that's one identity proven. I started out with the left-hand side, and I got to the right-hand side here. So that's simple enough. And let me show you, do I have time for 2 more identities? Or let me do just 1. And I think once I've done 1, the other one would be, you can kind of follow the same reasoning. And I think it would be good practice for you too. So I'll leave that for you. So the other trig identity that I say is one of the most useful in physics is the angle addition formula. So these are the angle addition formulas. This is how I usually remember it. Cosine of alpha plus minus beta is equal to cosine alpha cosine beta minus plus sine alpha sine beta. And there's a version for sine. Sine of alpha plus minus beta is equal to sine alpha cosine beta plus minus sine beta and cosine alpha. I probably don't have time to work out both of them, so I could probably do sine. So let me just pick sine and go with that. And this is where I do have to be a little bit careful in that. So starting from the left-hand side, I won't be able to really derive the right-hand side as I apparently did here. The expression for the right-hand side, it's quite complicated, and I'm not going to be able to just magically get to that. But what I can do is I can write down complex exponential version of the left-hand side, write down a complex exponential version of the right-hand side, and through a series of simplifications, I can show that they simplify to a form that are equivalent to each other. So that's what I mean, just proving the identity. So if I didn't already know the identity, then I can't derive it. So I can make up for lack of the knowledge of the identity itself there. But what I'm showing there is that whatever calculation it was that would have needed this identity, I could simply do the same calculation using the exponentials and exponential algebra. I didn't have to know the identity itself for whatever simplification it might have helped with. So let me write down the left-hand side. So sine of alpha plus minus beta in terms of the complex exponentials. So I'm kind of remembering the formula from before. E to the I times the angle. Yeah, I guess I'm going to keep plus minus throughout the whole thing. Alpha plus minus beta. Oh, and minus e to the minus I, alpha plus minus beta, divided by 2I. Okay, so that's the expression for sine. Let me do a little bit of simplification so that at least these things are all separated out. So I can distribute I into this parenthesis thing. And one of the rules of exponential algebra is that if you have e to the a plus b, then that's equal to e to the a times e to the b. So I'm going to write it out that way. So I have e to the I alpha times e to the plus minus I beta minus e to the minus I alpha times e to the, I guess, minus plus I beta divided by 2I. And I think that's where I'm going to have to leave it. I don't see any obvious way it would look simpler than how it appears now. So let me put a pause here for the left-hand side. And let me look at the right-hand side. I can write this out in terms of the complex exponential and see what I can simplify, and see if through a series of simplification steps, I can get an expression that I can look at and say, oh, that looks exactly like this. Left-hand side and right-hand side are equal to each other. So, so the right-hand side, let me just write down this as a reminder. It's going to take a little bit of time just to writing things down. I remember, was it a physics professor or math professor who said that his hand knows algebra better than his head? Sometimes it's a matter of writing things down, and it takes time to write them down. But once you write it down, then you can see how things might simplify. So let me do that. I'm just going to write out each term one at a time. So I have e to the I alpha minus e to the minus I alpha divided by 2I. So that's this done. This multiplies to cosine of beta, so e to the I beta plus e to the minus I beta divided by 2. Okay, that's done. Plus minus e to the I beta minus e to the minus I beta divided by 2I times e to the I alpha plus e to the I minus I alpha divided by 2. All right, so the thing to do is to expand the things out, hope that some things cancel out, and hope that things don't cancel out, that we'll be able to find the counterparts on the left-hand side. So I'm just doing the product. First term times the first term. That's e to the I alpha times e to the I beta. Oh, and the first term times the second term is plus e to the I alpha times e to the minus I beta. The second term times the first term is, yeah, it's not going to cancel out. I'm not that lucky. Um, minus e to the minus I alpha times e to the I beta. They don't cancel out because the exponents are different. Second term times second term, I get minus e to the minus I alpha times e to the minus I beta. Okay, that's the entirety of the first product. That whole thing divided by 4i. Okay, let's keep going. I have the second term. So second term is gonna be plus minus. Somehow this plus minus has to get transferred over to the exponent. We'll see how that happens. E to the I beta times e to the I alpha. Let me do a little favor to myself, and I'm going to order them so that alpha comes before beta. So that product is going to be e to the I alpha times e to the I beta. The first term times the second term is going to be plus e to the minus I alpha times e to the I beta. The second term times the first term is going to be minus e to the I alpha times e to the minus I beta. The second term times second term is going to be minus e to the minus I alpha times e to the minus I beta. The whole thing divided by 4i. All right, do some things cancel? Oh, you know what? I think which terms cancel depends on this sign here. I think that's how I'm going to get the plus minus in the exponent. So let me work out the couple scenarios. So the scenarios here is, let me take the case when it's plus. So when it's a plus, then the scenario I have is these two terms will add. This term will get canceled out by this term here. This will get canceled out by this term here. I'm trying to make sure that the exponents are the same. And this term will add to that term. Okay, so in that first case scenario, I have e to the I 2 e to the I alpha times e to the I beta. And then the last term, minus e to the minus I alpha times e to the minus I beta divided by 4i. Oh, and this is also 2. So the 2 cancels out, and I get 2i in the denominator. And this is the scenario that matches up if I had if I had this upper possibility, plus here and minus here. That's number 1. Let me write out number 2. So with the minus sign here, it changes which terms cancel. So I'm gonna have this term being canceled out by this, because with this minus sign, they're having the same sign, means they'll cancel out. So e to the I alpha minus e to the, so this will add to this term to get me 2 of the same thing. This term will add to this term to get me minus 2 of the same thing, and this term will cancel out with the last term here. So in that second scenario, I have the terms that are not canceling out, 2 e to the I alpha times e to the minus I beta, and this was the term that didn't cancel out, and I get minus 2 e to the minus I alpha times e to the plus I beta. I'm just making sure I note that it's not. Yeah, this was adding to this term. Yeah, okay, good. Okay, the whole thing divided by 4i. Okay, so 2's cancel out to get me 2i in the denominator. And if you compare the terms, this is what you get with the lower part of the sign, minus I beta here and plus I beta here. So yeah, the right-hand side is equal to left-hand side in both of these scenarios. So we've proven the trig identity, that's the angle addition formula for the sine. And it took a bit of time, it's kind of lengthy algebra, but the upside is that it's algebra. With algebra, really, the trait that's rewarded is attention to detail and not missing any symbols or signs, just going step by step slowly. And through all of these steps, I didn't really need to be creative about showing anything. And it's been a long time since I've read the proof of the angle addition formula, and I'm fairly sure the geometric proof is something that it takes so much creativity that I don't remember. I would have to look it up in a textbook. But proving it using complex exponentials, it's just following the exponential algebra. No creativity needed. You just follow the steps and you're done. And what this is showing is that any calculation that might have needed this trig identity, if you simply turn whatever trig expression you have into this complex exponential representation, then you can basically go through the steps that you might have gone through your trig identities. And at no point you needed to bring up the trig identities themselves. You can just go through the exponential algebra, simplify it down as much as you can, and that will be the simplest expression possible within restrictions. So yeah, that's the presentation of complex exponential representation of trig function.
So in fact, we are going to use this to kind of redo everything that we did before as anything that we used trigonometric functions to describe. We are going to instead use this complex number to describe them. So let me tell you what I mean. So this is how we describe the electric field from a single slit before. Let me do a quick comparison so that you have some sense of what this switchover involves. So comparison of real function representation and complex function representation. So before, this is how we expressed, well, this is how we express the electric field as being electric field as a function of position and time as, well, I'm just copying that over. E naught cosine omega t plus phi as a function of y. This is how we represented it, right? Now, this is the complex function version of this real function. I can use this complex function to do every calculation I did with this. And the complex function is this. E, the squiggly line is used to indicate that this is the complex quantity, so that people are aware of it. As a function of y and t, they are still real. So this is the magnitude, the length of the vector, E naught times, and this I would replace with the complex version, e to the I theta, I guess, so e to the I omega t plus phi as a function of y. Good? And I hope the relation operation to go from here to here is fairly straightforward. Let's say you start out by expressing things with a complex function, and then you decide you want the real version of that. Well, I think that's a fairly simple operation where you take this. Hopefully you have some numerical value of this, and all you have to do to get back to this is you take the real part, because that's what this is, and just discard the imaginary part. So that's something you can always do. Like, this is the freeway you get on, And you can always get off the freeway by taking the real part and go back to doing calculations using trigonometric functions. Yeah. Let me wrap up this particular set of calculation by telling you one more thing. So using this complex representation to represent real trigonometric functions, it works well most of the time. So for example, let's say you have these two functions. You have functions f and g that, it's some function of, let's say, time, and g is another function of time. And it could be f is equal to a cosine of omega t, g is equal to, b cosine of omega t. And you have the complex versions of those. You have the complex f, which would be a times e to the I omega t. And you have complex g, which is b times e to the I omega t. And most operations you can do, it works out the way you would imagine. So if you want to, so for example, here are some operations you can do. F plus g, f minus g, some scalar, c times f, all these, you can do the same thing here. You can calculate f plus g, f minus g, and some scalar c times f. But one thing that you are seeing me avoid doing is I'm not multiplying these two functions together. Because so when I've done all of this, the only thing that it takes for me to go back to this representation is I can take any one of this and simply apply the real, take the real part, and I'll be done. But when you're dealing with products, that's where things get a little bit complicated. Because if you do f times g, let me just do this quick demonstration. Let's say I do f times g here. So f times g gives me a times b, cosine squared omega t. Right? Nothing complicated. All right, let me do the same, and that's the real part, and that's all that. Let me just try calculating f times g. So if I do f complex times g complex, this is what I get. A times b, so far so good. And this is what I have. E to the I omega t times e to the I omega t. So e to the I omega t squared. Oh, I can simplify that. I know how to do complex, exponential algebra. So it's the e to the I 2 omega t. And when you take the real part of this, you get cosine of 2 omega t. Does that look anything like that? Yeah, so something has gone wrong, right? And it comes down to this fact. When you represent f as a1 plus ib1 and g as a2 plus ib2, any addition or subtraction you do, it doesn't mix real and the imaginary part. So real part is kept by themselves, imaginary part is kept by themselves. So you can just use that, and then when you separate the real part out again, then everything's fine. When you do, so this is actually the complex version. So what we want to represent with the f is just this. What we want to represent with the g is just this. But when you do f times g, that's when the real and the complex parts mix. Because a1 times a2, that is in my product. a1 times a2 is there, so that's fine. But I also have the imaginary part times imaginary part. Minus I b1, oh sorry, not minus. So I squared, which is minus b1 times b2. And it's the second term that causes issues when you are doing product. Having said all that, there's one particular operation you do with a real function that looks much, much simpler with complex exponential. We were actually doing this calculation before earlier. Where did I write it? I guess it's this one. It's a version of this one. This is a place where I had a function that's periodic, and I want you to take its time average. And I went through these, sophisticated formulas to get to a pretty simple answer, 1/2. And this is something that's proven in a math class that I want proof. So let's see. So this only works with a periodic function. If you have a periodic function of f as a function of time, and it takes this form of some constant times periodic cosine of omega t, and you can imagine doing let me call it this way. So some average of f squared. So the mathematical representation of that would be the 1 over t, what I wrote here, 1 over t, 0 to t, f of t squared dt, right? And in the complex representation, this can be written in a much more simpler way. This can be this. It's the complex representation of this function. So the complex representation would be a times e to the I omega t. Multiply that with the complex conjugate divided by 2. Gives you the same result as what you would get by going through the calculus. So whenever your final intended result is that you want to take the function, square it, and then average it as a function of time, then you can use this to really simplify your calculation. So I see that I have about 7 minutes left for the lecture today. In that remaining time, I can replicate this calculation using complex expression. So let me do that. So, sorry, I didn't organize my board very well. I guess let me leave this as a reminder of what we were just talking about. And I think I can use this space. So I really want to finish this because we are going to be using this, I guess, next week when we talk about intensity of a single-slit diffraction, because this is what will make the calculation much easier. So intensity of double-slit interference with complex exponential. So our starting place is this. We describe the electric field this way. Electric field as a function of position and time will be E naught e to the I omega t plus a phase as a function of position. And I can actually do one simplification already. I can explain to you what I was calling phase factor. It's called a phase factor because it is a factor. It is, let me write this out. It's equal to E naught times e to the I omega t to the exponential algebra, e to the I phi. So it is actual factor when you do it, properly using complex function. So this is the electric field due to slit 1, and electric field due to slit 2 is, I guess, E naught e to the I omega t, e to the I, so this was phi 1. So this would be phi2y. Good. And let me just quickly review the relationship between intensity and electric field. So in the complex version, this is what we would say for intensity. For the time averaged intensity, you can say that intensity due to slit 1 is equal to E1. And so I'm skipping a lot of numerical factors in between. E1 times the complex conjugate of E1. And because this operation already implies this time average done, you can see that a lot of things here cancel out. So E1 is all of this. E1 complex conjugate, you have E naught, which is real, so it's the same. But this is e to the minus I omega t, e to the minus I phi1. Those cancel out in multiplication. So this is simply E naught squared. Good? Or this is what we would call intensity, or this is the intensity due to a single slit. Or if there was only one slit ever, this is the intensity you would get. Yeah? All right, let's work out the intensity due to two slits being there. So intensity of 1 plus 2, that would be, all right, so it should look like E1 plus E2 times complex conjugate of E1 plus E2. Yeah? All right, let's write it out. I don't think I have to go through the, so before I couldn't do the whole thing all at once. I wrote it out into 3 terms and then wrote out, did this separately. I don't think I need to do that. With the complex representation, calculation becomes easy enough. I can just do it all in one shot. Let me write it out this way. So this is equal to this. So that's E naught, e to the I omega t that. E naught times e to the I omega t times e to the I phi1 plus E naught e to the I omega t times e to the I phi2. Right? That's this first term here. Multiplied by the complex conjugate, E naught e to the minus I omega t e to the minus I phi1 plus E naught e to the minus I omega t times e to the minus I phi2. I hope everyone's okay with this one single step simplification. I'm going to factor out E naught. Then I end up with E naught squared at the very beginning. Good. I have a factor of E naught from here, another factor of E naught from here. Good. And do everyone see that I omega t cancels out? Okay, so these will cancel out. And all I have to deal with are the phase factors. So that's a matter of writing out those 4 terms. So let me go ahead and do that. I have e to the I phi times minus e to the I phi1. So that's 1, right? This times that. Okay, 1 plus, let me do this one first. E to the I phi2 times e to the minus I phi2. It's also 1. So plus 1. All right, and now I have to do the cross terms. This times that. That's a plus e to the I phi1 times e to the minus I phi2. And this times this, plus e to the I phi2 times e to the minus I phi1. So I hope everyone recognizes these 2 terms from before. This is the constant 2 that was there before. And let me just do this last. Oh, I can't do this even in 10. I can't do this in 10 seconds. But let me write it out. So let me use this space here. Let me just go through this quick algebra. It won't take more than a minute. So this is the algebra for these 2 terms. Let me start by combining them. So it's e to the I phi1 minus phi2, e to the I phi1 minus phi2 plus e to the I phi2 minus phi1, e to the I phi2 minus phi1. I'm just going to notice something here and realize that this is minus 1 times this. Right? So I can actually write this as a minus phi1 minus phi2. Yeah? Calling this whole thing x, this whole thing x, then this is what it looks like. It looks like e to the ix plus e to the minus ix. That would be this, or the numerator of this. So what I can say is, using this, I can say this is 2 times cosine of phi1 minus phi2. Yeah. So substituting this in for this, I get e naught squared times 2 plus 2 cosine of delta phi. And that's the exact same result I got before using the real trigonometric function. The difference is that this is a lot shorter. It's a lot easier. The introduction of the tool, it maybe takes longer, but the difference is, you'll be, if you're working in engineering or physics, you'll be using these tools a lot. When you go into Fourier analysis, this is the tool you are using. This is one single powerful tool. It'll take time for you to learn, but once you learn it, it'll make this job so much easier. Whereas if you keep using the old, outdated tools that you knew when you were in high school, your whatever task you do continue to be difficult. It's a difference of using, hammer and nail to build a house versus using power tools to build a house. So. Good. So, all right. I still have enough time to do the rest of the topics today. Sorry, it wasn't quite 5 minutes, but I needed a reminder of this so that I can use that for a similar calculation today. The conceptual ideas that we will cover today, they are, do everyone feel like you got, this complicated mathematical calculation, if it takes you a while, great, that's what homework is for. So let me see if this idea here, that the pattern you see with the double-slit interference, that it comes from the phase difference between two beams, and that phase difference is due to this path length difference. That basic idea, is that clear to everyone? Yes? Like, none of this sounds mysterious? Yeah, once that's clear, then diffraction that we are going to cover today, the conceptual part of it is actually no more difficult than that. There's a little neat trick that you need to introduce, but other than that, it's actually, I'm forgetting the word. You can get it. There's nothing stopping you from getting it. I do need to remind you of one thing, is Huygens principle. I think it'll be easier once I have a drawing. Let me give you a picture of single-slit diffraction from the textbook. So with the single-slit diffraction, this is kind of what you are going to see. You have some light that's going through a single slit. So this is the diffraction grading that you have seen last time. One of the rows is a single slit. And when I put this through one of the wide slits, then nothing happens. Well, it spreads a little bit. When it goes through the smaller and smaller of the slit, you start to notice more of the spreading of the light. Even from far away, you can see the spreading of the light, right? Now, if you are closer, what you would see is that there's a repeating pattern of bright and dark fringes. And here, this row, it's one slit. It's not double-slit interference, it's just a single slit. And that's what this picture here is showing. This picture from your textbook is showing that you see that happening. When light goes through a single slit, you get a feature, this destructive interference here, that you would only say is from a result of interference. So what's interfering with what if you have only a single slit? Like you have one slit, there's no other slit that it's interfering with. So where is this destructive interference coming from?
Reflecting from the size of the slit.
So you do want to pay more closer attention to the slit now, right? What's happening to the slit? So this is where I need to remind you of Huygens principle. It was mentioned in chapter 1, was way back when, and we didn't do anything with it. That's why I need to remind you of it. So let me use this picture to remind you of it. If we have light that's shining in from plane wave coming in from side, this is how I might draw it. You could draw it with these wave fronts that are coming in, and as it goes through the slit, initially only this portion would get through, right? Now, if this is how you are visualizing this, then from this alone, you wouldn't really get why it should. Maybe you get intuitively that it should spread out. Maybe you get that far, but even then, what's not clear is why would you get destructive interference somewhere? So let me go into the more details of Huygens principle. What Huygens principles, by the way, I'm not good with the names. Almost all the physicists' names I pronounce in this class will be wrong. When I say de Broglie, I'm pretty sure that's not the correct pronunciation of the French physicist's name. So anyways, so the Huygens principle says, this is what it says. It says that when you have this wave front, it says that each one of the points on the wave front acts like a source of point source of wave. So I could consider this single point here as a point source that's causing I guess waves that look like this. And I can consider this source as a source of wave that's causing waves that look like this. And I can do it for an infinite number of points. And to construct this wavefront that you see here, what you would have to do is you have to imagine what is the result of all these different contributions adding. So you kind of draw the lines along that rise to the top. That's what gives you this. From the plane wave, you also get a plane wave. Now, when you have a slit, so it was an infinite plane wave before. Now it's not. So now there's a difference. When you have, for this point source at the very left end, when you consider that to be producing this wavefront here, in this portion, there's no comparable point wave source here that's going to essentially give you a flat line again. So that this gives you a picture of how wave sort of bends around. Because so in the middle portion, you can still get a flat wavefront, but towards the edge, it kind of bends. So that's qualitatively how it's spreading out. But let me show you how this is mathematically useful. Instead of treating this single slit as a single light source, we can imagine it as an infinite number of light sources. So instead of wondering where is the other light source that the interference is coming from, we can consider interference between two different locations of one slit. So that's what we are going to do. And the next step is a little bit of a mathematical trick that no one's going to guess intuitively. So let me give it to you. So this is a way of explaining why we see this interference minimum where we sit. So this is how you would analyze it. If you look through the textbook, you will eventually see this. So I have all these. I can draw infinite number of point sources. So I'm just going to draw a few of them. So we are looking to see which one of these. So how should I put it? so for the light that's arriving there from each one of these sources, so there's light arriving to that spot from each one of these point source locations. Would it be fair to say that all of them are destructively interfering with each other? At this location where, the intensity is 0, like that's the result you would get if they were all adding up to somehow 0, right? So the question is, how are they adding up to 0? So the way we are going to do it, we are going to find the pairs that somehow cancel each other exactly. And once we then move those pairs through the whole slit, then that explains why it's destructively interfering here. So for this first diffraction minimum, the way you find the pair is this. You imagine breaking up this slit into two halves. This portion, upper half and the bottom half. And what I'm going to try to say is that this portion, light coming from this portion, will be destructively interfering with the light coming from this portion. I guess this drawing is too small. I can't really draw anymore. Let me now erase this board so that I can draw a bigger picture and show you the geometry for figuring out the phase differences. And we'll go through the same type of argument we did in the first 5 minutes of this class to see what that angle should be. So this is the single slit. I'm going to use a different letter from the textbook because this is the letter your lab manual uses, A. Hopefully that's not too confusing. And so we are imagining a screen that's very far away. When I draw the light rays, I'm going to draw them parallel because I'm imagining a screen that's very, very far away. So let's say that I have this infinite number of sources. And I'm saying that for the angle theta of the path of the beam, that represents the first minimum, that I can pair this source with this source here, halfway across the slit. I'm saying that I can pair these two together so that they destructively interfere. So we go through the same geometry argument as we did for the double slit. So they are parallel rays. Drop down this perpendicular line. So given this theta here, that theta is the same theta here, right? So this path length difference. What is the smallest path length difference that would give me destructive interference? Half of the wavelength, right? That'll give me the pi phase shift or half of cycle. So I want this to be half of the wavelength. All right. I guess I have everything. So based on this geometry here, this hypotenuse is half of the slit size. So the half of the, that's hypotenuse, half of the slit size, times the sine of the angle, sine theta 1 is equal to this. So, so then I get for diffraction minimum, that's what we call it for these locations of destructive interference. We're going to be a little bit sloppy with the word diffraction and interference. It's just going to be that way. So for diffraction minimum, it'll be A over 2 sine theta 1 is equal to lambda over 2. A sine theta 1 is equal to lambda. All right. So these two destructively interfere. Will these two destructively interfere also? Right? So you can say the same thing for every one of these as you move down across this slit, which means the so you are adding up infinite number of zeros, so you get 0 in the end. Now, with the diffraction, the argument for the next order. So because when you see the diffraction pattern, you don't see just one. You see the next one, and then the next one, and then so on. So, so I need to find more than one minimum. I need to find a whole series of minima. And when we are doing it for double-slit interference, the way we did it was we considered the path length difference that was longer, right? If we had half of the wavelength, then you consider 1.5, 2.5, 3.5. With the diffraction, we are not going to do it that way. It comes down to, it's not a clean argument if you want to make it that way. It's not, yeah, anyway, we're going to do it differently. So we will actually keep this portion of the argument the same as we consider next diffraction minimas. That the path length difference will keep it at 1/2 of the wavelength. What we are going to change is how we are breaking up this slit. So for the next diffraction minimum, what we are going to do is instead of imagining breaking up this slit into 2 halves, we are going to imagine breaking it up into quarters. So imagine having this broken up into quarters. Then you can see that if I'm trying to get the same length, this angle now has to be bigger. It has to be going at some angle like this. I don't know if I'm doing it right. So drop down something perpendicular, and this will now be delta x, right? And let me write down the relationships for that delta x using different color. So for this new delta x, I guess it is the same delta x. So for that delta x, what I can say is that that's equal to the right-hand side. That would be the quarter of the slit size, a/4 times the sine of, this is the second minimum. And the left-hand side, it's going to be the same length, λ/2. So for this second minimum, what you see is, so multiply through by 4, I get a sine theta 2 is equal to 2 lambda. So do you see the pattern for what the diffraction minimum? So this would be the destructive interference for single-slit diffraction. Single-slit diffraction should look like in general case, looks like everything stays the same. So this is the number that should change. Any suggestions? So n, integer n, right? So 1, 2, 3, 4. You can imagine continuing this argument forever. So for the general formula, we would say for diffraction minimum, it's n, and that n goes from 1, 2, 3. Now, could this n be 0? Yeah, n equals 0 gives you something different, because when n equals equal to 0, that's when angle is 0. Well, you have a maximum there. You don't have minimum. So here n only goes from 1 to 3. And if you want, you could say plus minus, but sort of not super necessary. So this is the condition for destructive interference for single slit. As you can see, once you get that little nifty mathematical trick about considering the entire slit but breaking it to halves and then pairing up finding the pairs that will destructively interfere, then the rest of the reasoning is exactly the same as double slit interference. And for finding this minimum, it works out great. Now, while we have this expression up here, I want to bring your attention to this so that this won't confuse you in the future. So this is the expression for where you have destructive interference with a single slit diffraction. I want you to look at these expressions that we had for double slit interference. Let me hide this. What is this? What does this expression describe? Does this describe destructive interference or constructive interference? Yeah, constructive. But it looks exactly like that. It's very easy to get them confused, so please don't get them confused. The argument leading to each of these formulas are they are different. That's why it's important for you to know the argument rather than trying to simply memorize the formulas, because then eventually you'll get this confused with that, which are entirely different in almost every sense of the word. All right, so I have 10 minutes. So I have 10 minutes of lecture remaining. What I would like to do is I want to do my version of this derivation that's done in the textbook. And so that you know where it is. In your textbook, it's in the section 4.2 of the textbook. And this is how they do it. They do it using some phasor diagram. And it takes them very long time to work through. You can read through it. And I think it'll be good exercise for somebody to read through it. So do that. But I can tell you this. There's no way I can do this in 10 minutes. Where's the result? OK, so that's the result that they obtain. There's no way I can do that in 10 minutes. What I'm telling you now is I can do it in 10 minutes using this formalism we introduced the last time. So the reason that's such a complicated, long, difficult argument is they have to do it geometrically. They have to draw phasors. They have to do all that. And it's a lot of work. It takes a lot of time. But one thing that's I don't know, almost magical about the complex exponential is it provides a very natural bridge between algebra and geometry. I showed you how this gives you meaning to the complex plane. So let me use this tool to do this calculation. So this is the argument that we are going to make. So let's say intensity of single-slit diffraction. And you do have to, set up the physical situation, because simply writing down expressions that don't mean anything doesn't actually help. So for intensity of single-slit diffraction, this is the setup that I'm physically imagining. I have a slit of size A. I'm going to use the same letters here left. And I'm considering the light rays that are going to some screen very far away. And so this time, because I have to consider arbitrary angles, I can no longer make that argument about breaking this up into some even number that will pair up into destructive interference. I can't do that. I want some general expression. So let me just label a few things. So these light rays, they are going off at some angle theta. And that will correspond to this light landing on some spot on the screen somewhere. Yeah? And conceptually, I think this is how I can do it. So if I could somehow calculate the total electric field of all these, arriving with the different phases, added up together, and I take that and square it, then that would be my intensity. Right? No? Yeah, and so conceptually it's pretty simple. You have all these different light rays contributing some amount of electric field, add them up, square it, you get intensity. Yeah? And so this total electric field, so with the double slit, we added two expressions for electric field. So here it would be, I guess I could write this as a sum of small contribution. I don't have a proper letter for this. Well, I guess I could label each one of these rays 1, 2, 3, 4, 5, and so on, goes up to some big number n. And I could have contribution from each one of those electric fields. I goes from 1 to n, add them up. That'll be the total electric field. That's the superposition principle, right? Now, that could give me some approximate formula. But I don't want anything approximate. I want exact formula. What's the step that goes from this approximate total electric field to an exact expression for electric field?
Infinity.
So you make the number of rays infinite. So in your math class, what did you call that? Integral, yeah. So yeah, this is the Riemann sum. And when you turn that, make the Riemann sum exact, that's the integral. So that's what I'm going to do. I'm going to represent this instead as I have a small contribution to the electric field. And let me use this parameter to label it. So let's say this is my x-axis, and my x starts from 0, goes to some value. So this small contribution to electric field will be parameterized with x. And I integrate this from x equals 0 to a over the entire slit. That should give me the exact value of the total electric field. And when I square that, that's what gives me the intensity. So conceptually, it's actually a pretty simple calculation. What you will realize that when you try to do this with the real functions, the math will just overwhelm you. And this is where I'm claiming that if you use complex exponential, you can do this calculation in the 4 remaining minutes. So let me do that. I'm going to express, I'm just imagining some electric field from one spot there, that I'm going to express that small contribution to electric field as some amplitude times e to the I omega t, that's the time-dependent oscillating part, times e to the I some phase factor that's going to be a function of x. And let me go actually one more step. I'm going to, this time, because I have to do the integral, so I kind of have to know the expression, I'm going to write down what this is. And I can write it down from the geometric consideration. Let's say this is at some point x away from here. Then you do the same thing that we've been doing before. This path length difference, I don't know, lowercase delta, that's x times sine theta, path length difference. That is the path length difference. So that'll give me the phase factor of, x sine theta divided by lambda times 2 pi. That's my phase factor. Good? All right. So let me actually write that out. So that's equal to E naught e to the I omega t times e to the I 2 pi over lambda times sine theta x. All right. So this is my expression for infinitesimal contribution to the electric field. Let me integrate. So for the total electric field, what I need is I need to integrate. Integrate it from x equals 0 to a. Integrate it with respect to x from x equals 0 to a. Good. Now, because these are all exponentials, this is actually a remarkably simple integral, even though it looks complicated. This is constant, constant. Here, everything is constant except for x here. Meaning, this is the integral. When you do the integral, you get this. E naught e to the I omega t, that was, constant. And this, so I need the integral of this, which would be, to remember the antiderivative. So it would be lambda over I times 2 pi sine theta times e to the I 2 pi over lambda sine theta x. Did I do the antiderivative correctly? Okay. Evaluated from 0 to a. So, so when I plug in a, this is what. So let me write out what's evaluated. Oh, I may have underestimate time needed. So E naught e to the I omega t times lambda over I 2 pi sine theta times, plugging in a, I get e to the I 2 pi over lambda a sine theta, I 2 pi over lambda a sine theta. And then plugging in 0, I get 1. E to the I 0 is 1. So minus 1. So this is the expression we get for the total electric field. And since it does seem like I'm out of time, let me tell you what needing to be done, and just let's get a sense of if you feel like you can do it. Since I'm out of time, sorry. I need 2 more minutes to actually finish the calculation. So before, with the real functions, what we would need to do is we would have to square it and then do the time average, right? Using this special case, all we need to do is take that, multiply with a complex conjugate. When we do that, actually, some of these are going to go away. E to the I omega t, that's just going to be 1. I times minus I, that's also going to be 1. So a lot of these will simplify. You will still have this dependence on theta that's kind of a little bit weird on the outside. And the most complicated part algebraically will be working out this portion. This times its complex conjugate. Does that feel like something you can do maybe in 5 minutes? Yeah. And what I'm telling you is when you do that, you get the resulting expression. Compare what you see with one of these two. You'll get cosine theta by doing the comparison. And that will be the same result that's in the textbook. And it didn't quite take 10 minutes, but I could have done it in 15 minutes. And so this is the reason I introduced the complex exponential early. And you will see these complex functions more later in the semester when we do quantum mechanics. So it's good to get used to now. So let me finish up that lecture by calculating the expression for intensity. And when you finish the integral, this is the result you have, that the total electric field that you get. And this is the part that your textbook has to use the phasors to describe what the sum of all the optical electric fields will look like. And here, I just use calculus. Just do the exponential, find the antiderivative, evaluate it at the limit. And when you finish all that, this is what you get. That's equal to intensity. I think the way I defined E naught is, I think I'm missing some symbol here. I'm trying to say, I think I did a little bit of notation abuse. So there's some step here that's not super kosher, but I think in the end, the way I've written this E naught here, that's the optical electric field you would have had. Yeah, the units don't quite. Oh wait, if the units don't match up, then I do have an issue. Yeah, okay. There's a problem here that I need to fix. So the part about units not matching up is if I'm okay. So let me just write here what the correction would be, and I'll write the version with the correction. So I think there's a slight bit of a mistake there, which is that so I'm trying to write down this small contribution to the total electric field here. And in writing out this integral, I've written this out as the E naught. And I think E naught is meant to be the E naught would be, let's say, at the center where everything is in phase. No, so E naught is meant to be the E average, or without interference. And if I have E naught times the dx, and I integrate over different values of x, then that doesn't give me something that's quantity of electric field. That gives me a quantity of electric field times length. That's what this dx is.
So what this coefficient here really should be is some kind of electric field density. So what this really should be is E naught divided by A, so that I'm acknowledging that I'm taking contribution for, so this has to be some kind of a density, so that when I multiply to dx, I'm getting a portion of the electric field contribution that's attributable to this dx. And so, when I add them all up, then I get what I should get. So there's a missing factor of A there. So let me carry that through. There should be A here, and there should be A here. And that'll make the units come out right. I have a unit of electric field from here, and everything here is something that cancels out to a unitless quantity. So let me make that correction just on the fly here, and write down the version of the total electric field that has the correct factors. So it's E naught times e to the I omega t times lambda over, let me put A in some place. Well, I'll put A here. A times I 2 pi sine theta times, and so I have parenthesis e to the I think that's 2 pi over lambda times A sine theta minus 1. Okay, so that's the, this is the total electric field. That's what this says there. So what I want to do now is I want to finish up the calculation, derive an expression for the intensity, compare that to the formula that's in the textbook. So this is the derivation that doesn't require any use of explicit geometric reasoning, just as long as you watch the units and set up the integral correctly, let you finish the calculation with just simple calculus and algebra. So starting from here, what I want to calculate is this. So now one thing that I will bring in is, so here you see that the electric field is a function of time, and your intensity technically would be a function of theta at what angle it's going, and it would be a function of time in the strict terms. But especially with the light, instantaneous intensity is something that we are very seldom interested in. We are usually interested in the average intensity, averaged over time, and it'll still be a function of theta. So, which is fortunate, because instead of, if we are interested in the square of this, then given a complex representation, I think I have a lecture somewhere about how you can square this and expect to get the things right. But in the limited case, when your function, this complex function of time is an oscillatory function of time, and all you are interested in is the time averaged quantity, then I can use this special expression that this time averaged quantity will be equal to, or I guess what I really should write down is, so if I have electric field as a function of time, and what I'm really interested in is not just the square, but this square or averaged over time, then this can be simply expressed in terms of this complex function as the complex conjugate of the function times the complex function divided by 2. When you work this out, you are going to get an expression that doesn't depend on time anymore, and this will be the time averaged of E squared. So I'm gonna do the calculation. I have this expression for E total. Let me calculate the time average of that. So I will have time average over time. of e as a function of time times e as a function of time to itself. So that's gonna be, with the use of this relationship in mind, it's gonna be the complex conjugate of the function times the function itself. So let me write this out. This is the function that I first have to take the complex conjugate of. So let me write down the complex conjugate of this function here. So it's e naught times e to the minus I omega t times lambda over a times, oh, I have I there, so minus I times 2 pi times sine theta. I still have this. I need a complex conjugate of that. E to the minus I 2 pi over lambda a sine theta minus 1 times the function itself. And the function itself is e naught times e to the I omega t times lambda over a I 2 pi sine theta times e to the I 2 pi over lambda a sine theta minus 1. All right, I'm just staring at those symbols to see what will cancel out. I think I see this canceling out this. So let me cancel them. And I guess I'll collect the coefficients in front first, and then let me try to work out these two products. So the coefficient in front is gonna be e naught squared times lambda squared divided by a squared. Oh, minus I times I is 1. So don't have any minus sign. So I have a squared times 2 pi squared times sine squared theta. All right, I got that. Times. And I have this complicated looking product. Let me expand it out and see what I get. Maybe it'll simplify somewhat. So I have the first term times the first term. It's 1 because it's the same exponent except with the different signs. So I have 1. And the second term times the second term is plus 1. So, okay, plus 1. And I have the cross terms. This times the second one. So that's going to be minus e to the I 2 pi over lambda a sine theta. And the second term times the first term. Oh, that's another minus. Oh, wait, sorry. The first one, I forgot about this minus sign. So there's a minus sign there. The second term is just going to be minus e to the I 2 pi over lambda a sine theta. Oh, I think I see some simplifications. So this reminds me of something I've written before, which is that cosine of theta is e to the I theta plus e to the minus I theta over 2. So if I imagine factoring out minus 1 from both terms, then this is what I have. So this combination of terms here, that's very close to this cosine expression. So I can actually rewrite this into something that involves cosine. I think it's going to be 2 times cosine of this parameter here, 2 pi over lambda times a sine theta. Okay, that's getting somewhere. So this is, I think I'm close to the end here. Let me write down the final simplified version here. It's gonna be e naught squared lambda squared over, feel like there's some, let me keep it this way for now.
I have 2 pi squared times a squared sine squared theta. And I have this 2 thing here, so let me pull that out. 2 times 1 minus cosine of 2 pi over lambda a sine theta. Okay, let's just do a quick sanity check. One thing I want to make sure that this expression does is I want to make sure that when theta goes to 0, this expression will be at a maximum. So when theta goes to 0, I think we might be better off trying to simplify this further. Because when theta goes to 0, I think I have 0 over 0. And I don't want to have to deal with the L'Hopital's rules and whatnot. I could simplify. I think there's a power raising formula. So from this, you can get that sine squared theta is equal to 1 minus cosine of 2 theta over 2. So this is one of the trig identities that allows you to trade a double angle with raised power. And what I'm going to do is I'm going to identify this as my theta, quote unquote. With that identification, I can rewrite this quantity here as sine squared of this theta times 2. I think that's what that is. So can rewrite this as 2 times sine square of this thing, pi a over lambda, and there's a nested sign. I'm not gonna be able to get rid of that. Sine theta. Okay, so that lets me simplify a little bit, and I can just finish writing this down. I got a lot of factors of 2, so let me cancel out some of them. I have 2 times that 2 there, and I have 2 squared, so they will all cancel out and leave me with e naught squared lambda squared over pi squared a squared sine squared theta. And I think this is where you kind of begin to recognize some common term here. And if I look up the textbook formula, I'm pretty sure this is the one that they label beta. So so let me use that and just to write out. I have e naught squared times sine squared beta divided by beta squared. So this is the derivation that you end with going through the consideration of a single slit diffraction using the complex exponentials. And so this is the formula we end with. Let's compare that with what your textbook says. See if we are close. Let's see here. Yeah, so this is the beta that we defined, pi times a over lambda times sine theta, where the theta is defined the same way we defined it. It's the angle at which theta is, they don't have a figure. It's the angle at which the light is going. So it's the same theta that I represented here. And when they work out the intensity, they have this I naught. So we identify that with this E naught squared here. That's gonna be our intensity at the central maximum. And I have the sine beta squared divided by beta squared. So this is the derivation.